The GitHub repository for trading agents currently sits at 54,500 stars and nearly 10,000 forks. The framework simulates a complete trading floor by populating it with specialized, autonomous AI analysts working in tandem. Instead of dumping massive amounts of quantitative data into one large language model and hoping for a coherent result, the system routes data to specific agents, forcing them into structured debates to reach consensus. The underlying framework driving this architecture was published in a December 2024 technical paper on Archive. Decomposing the analysis into specialized roles that challenge each other provides a level of logical verification that monolithic context dumps cannot match. This diagram illustrates the standard approach to AI trading over the last few years, cramming raw JSON feeds, historical price data, and news articles into a single language model. That method creates immediate structural problems. The model forgets earlier instructions, its context degrades rapidly, and it often gets caught in infinite logic loops trying to reconcile conflicting signals. If the provider's API drops a connection mid-analysis, a standard script crashes entirely. Every token processed up to that point is lost, and the entire computation must be restarted. TradingAgents utilizes state mechanics that allow it to survive a total network drop without losing its place in the workflow. Stateless, single-prompt models lack the architecture to manage the multi-step reasoning required for consistent algorithmic trading. This network graph represents LangGraph, the state machine powering the framework. Unlike early AI tools that ran in unbounded loops, LangGraph enforces strictly bounded workflows, where each node has one distinct job. Here, the fundamentals analyst node looks only at structural data, evaluating company financials, performance metrics, and intrinsic value. In parallel streams, the sentiment analyst scores social media mood, while the news analyst parses global macroeconomic indicators to gauge real-time events. Finally, the technical analyst calculates specific market indicators like MACD and RSI to forecast short-term price movements. By dividing the cognitive load 4 ways, the system ensures each model only interacts with the specific data relevant to its domain. Segmenting the workload ensures each model processes only its designated data, significantly reducing the risk of context degradation during the ingestion phase. Once the 4 analyst nodes generate their reports, those documents are forwarded to a specialized researcher team. This team contains a bullish and a bearish persona. These opposing models process identical data and actively challenge each other's assumptions before generating execution signals. They must formally defend their arguments, balancing potential upside against specific risks identified in the data, before presenting a case to the portfolio manager. The portfolio manager reviews the debate transcript, assesses the strength of the adversarial arguments, and makes the final call to execute or reject the trade. Forcing agents to argue against an active detractor prevents the system from blindly following noisy market data, acting as a built-in filter for hallucinations. The multi-agent debate creates a strong analytical baseline, but the system's persistence mechanisms maintain integrity during volatile runs. In pull request 594, the maintainers introduced a line graph checkpoint resume feature. This diagram illustrates the recovery process. If an API rate limit triggers a crash halfway through, localized SQLite databases anchor the exact failure coordinate. The framework resumes from that checkpoint, completing the sequence instead of discarding prior steps. Beyond crash recovery, the framework maintains a persistent decision log. When evaluating a ticker, it automatically fetches the realized returns of its own trades. By comparing those past decisions against the S&P 500, the system calculates whether its previous strategy generated true alpha. It then generates a reflection on those outcomes, injecting the lessons learned directly into the portfolio manager's current prompt. Integrating stateful checkpointing with a realized return memory log enables the system to evaluate its own performance and apply those corrections to future tasks. Deploying this in a production environment is handled through a strictly provider-agnostic .env configuration. This layout lets you route tasks by cost. You can assign the heavy reasoning of the portfolio manager to the GPT 5.4 family, while offloading high-volume data parsing to DeepSeek or Qwen. For firms handling sensitive enterprise data, the entire pipeline can be routed through local Llama instances. There are inherent limitations to this approach. The non-determinism of language models makes exact backtesting replication difficult to achieve. Furthermore, running multi-round adversarial debates across 5 different agents requires significant token consumption, driving up API costs on every tick. While TradingAgents is a robust research framework, scaling it for live execution demands strict architectural planning to manage the resulting token overhead. Consider how these mechanics apply beyond finance. This same adversarial multi-agent architecture could be applied to automated incident response or complex cloud infrastructure provisioning. Pairing structured, bounded debate with persistent memory creates a baseline for resilient AI systems across any technical vertical. If you want weekly, rigorous breakdowns of the engineering tools pushing these boundaries, subscribe to the channel. Click the video on your screen now to see how other agentic workflows are being deployed in production. Advancing agentic engineering requires moving beyond prompt refinement into the design of complex organizational logic for AI.